Alrighty, so before we switch gears, we want to talk about one more application of the derivative. And this is actually an application that we've talked about before, but we have a good bit more to say about it and kind of setting up for the rest of this course. Okay, and that idea that we're talking about is antiderivatives. So let's just first of all review what we mean by antiderivative. Now, differentiation is a type of operation. It takes a function, like x squared, and takes its derivative and outputs a new function, 2x. An antiderivative is just kind of like the opposite operation. So you start with the function 2x, and you find an antiderivative, x squared. So to be a little bit more precise, recall that we say f of x is an antiderivative of a function f of x on some open interval, ab, if f prime of x equals f of x for all x in ab. So of course, we require that this capital F, this antiderivative, be a differentiable function. And so its derivative at each point over an open interval is just f of x. Okay, and so what we can say is that for such a function, capital F of x, to exist, given a function little f of x, it's enough to just say that little f of x is continuous. And that's all we'll say about that for now. But remember, another important note is that we're using this word an, which implies that antiderivatives are not unique. And this is pretty easy to see because if I add any constant to an antiderivative, so for instance x squared is an antiderivative of 2x, well x squared plus 1 will also be an antiderivative of 2x. And what we know more specifically is that by the mean value theorem, so as a direct consequence of the mean value theorem, so this is mean value theorem, MVT, antiderivatives for the same function will differ by a constant. And so more precisely what we mean is if f prime of x is equal to g prime of x, so if two functions have the same derivative, then f of x must be g of x plus some constant c, so just some fixed number. And now this is, of course, over whatever open interval we're considering. So if f and g have the same derivative on an open interval, then on that open interval, f will equal g plus a constant. Okay, and we actually verified why this is the case. So it was actually enough to show that the derivative of a constant function on an interval ab, if it's 0, then that function has to be constant. Okay, so it looks good. So this is just kind of a quick review of antiderivatives. And now we're just going to kind of reformulate the idea of finding an antiderivative in a couple of different ways. Okay, so now we want to talk specifically about when antiderivatives will exist. Okay, and we mentioned this before, but if f of x is continuous, and now I'm not going to specify an open interval or anything here, I just mean f of x is continuous over its domain. Now you can just think about its domain as being an interval or a union of intervals like we've done throughout. Then f of x has antiderivatives. But moreover, we want to give a name for the most general antiderivative. So that way, when I say, okay, what is the antiderivative of f? Well, I can't say specifically which one it is, but I can give a general form for the antiderivatives of f. So we give a name to this. We say the indefinite, and now you're just going to have to go with me on this notation or this terminology for a while. It's going to all make sense in time, but for now, we're just defining this thing. It's called the indefinite integral. Okay, indefinite integral. Now later on we'll talk about something called the definite integral. That's why we're specifying, okay, this is the indefinite integral of f of x. Is the most general form of an antiderivative of f. And we're going to denote it in a special way. So we're going to make this curly S. Okay, so it really is an S. When you see it for the first time, if I didn't tell you it was an S, you may not actually guess that it is an S. To me, it's always looked more like a forte symbol. So if you have something like this, so if you know anything about music or if you looked at sheet music, this is like a forte. Okay, but that's not what we're talking about. Okay, so it's an integral sign is what it's called. So this is an integral sign. And then you put the function f of x and then dx. Okay, and okay, so this is the most general form of an antiderivative. So this should equal, this is just the notation that means take any antiderivative and add an arbitrary constant. Okay, so we have a little ways to go with this notation. So the function f of x that we're finding the indefinite integral of is called the integrand. Okay, and then this dx, and I promise this will all start to make more sense later on, but for now, this dx, we just say that this specifies the variable of integration. Is x. So if it was dy, if it was like f of y dy, then this would be specifying that the variable of integration was y, okay? And now realistically, it's not going to be too big of a deal to really think much about this. But later on, if you take multivariable calculus, you look at things like double and triple integrals, and so it becomes very important to think about what is the variable of integration. But for now, this notation, it's just one of those things you just accept for now. Okay, so all of this nonsense, integral sign of the function called the integrand that we want the indefinite integral of, with this dx, and now this dx is like a differential, okay, but that's, again, we'll get to that when we get there. But the point is, all of this is equal to f of x plus c, where this f of x is any antiderivative of f. And then finally, the plus c is an arbitrary constant. Okay, so one of the tricky things about calculus that we've already encountered is that, okay, we've learned this thing called an antiderivative, and then we just sort of make it really, really complicated by introducing a different name for it, the most general form of the antiderivative. We give it all this notation, we soup it up, and you say, why in the world are you doing this to me? Why are you trying to confuse me? Well, the thing that's going to happen is we're going to look at the definite integral, which is going to be somehow completely unrelated to the indefinite integral, but it's going to turn out that they're actually not so different. So the notation here is already kind of foreshadowing the connection with the definite integral. Okay, and it's one of those things, just for now, just know when you see this integral sign with a function with a dx, all it means is find an antiderivative of this function and then put plus c. Literally write just plus c after the function. That will be the most general form of an antiderivative of f. Okay, so you got the idea of an indefinite integral. It's just the most general form of an antiderivative. So we're also going to introduce one other concept, and that's the concept of a differential equation. So a differential equation is an equation relating a function to its derivatives. Okay, so this is a little vague, and it's intentionally vague because actually the study of differential equations constitutes its own course. I mean, there's just countless applications of differential equations. And in fact, there's even kind of another branch where there's an entire course on what's called ordinary differential equations. That's more closely connected to what we're doing in Calc 1. But then there's also something called partial differential equations, and it's okay if you have no idea what that means, because it's going to require first defining what a partial derivative is, and that's a concept in multivariable calculus. But we're just working with single variable calculus. So probably what I mean to define here is actually an ordinary as opposed to a partial. So again, for those of you that are moving on and taking more advanced courses, this will be relevant to you. It'll be one of those things that I'll say it now and it won't really mean anything, but when you hear it again, at least you've heard it before. So we're really talking about ordinary differential equations here. So just one independent variable. And so, for example, we could have that dy dx is equal to x squared plus 4x. Okay, so we want to find y, which is a function of x, satisfying this equation. And now this equation is called separable. Okay, so what I mean by separable is sort of like this terminology ordinary and partial. It's something that maybe is not so relevant right now, but the result is that because it's separable, and maybe one day you'll learn specifically what that means, is that we can just solve it by finding an antiderivative. Okay, so in other words, we see that y is just going to be an antiderivative of this function. So what is an antiderivative of x squared plus 4x? Well, it looks like maybe x cubed over 3. Okay, so if I take the derivative of x cubed over 3, I'll get x squared, and then plus, 4x. So if we have 2x squared, the derivative of 2x squared is 4x. Okay, so that's an antiderivative. But now we have to remember that the solution to this differential equation may not be unique, and in fact it's not. So in general, we'll have this plus c. Okay? But now, let's say that we have something called an initial condition. So what if x equals 0, what if y equals 0 when x equals 0? Okay, so maybe I know something about this function other than just the fact that it satisfies this differential equation. Maybe I know something called an initial data, right? So I know some initial information about y. Well, in this case, this is what's called an initial value problem. Okay, so an initial value problem is just a differential equation that gives some initial information or some point on the graph of the function that satisfies the differential equation. Okay, so if I know that y is 0 when x equals 0, if I plug in 0 for y and 0 for x, so this will be 0 cubed over 3 plus 2 times 0 squared plus c, I see actually that c is equal to 0. So the solution to my initial value problem, which this whole thing is my initial value problem, is y equals x squared over 3 plus 2x squared. So in other words, I've found the specific antiderivative satisfying this differential equation that's separable, that also satisfies this initial condition, that y equals 0 when x equals 0. That's what a typical initial value problem entails doing. All right, so the instructions here say find an antiderivative of the following function. Now, it doesn't say find the most general form of an antiderivative. It just says find one of the antiderivatives. Okay, so let's do that. Now, this first function, f of x, is just a polynomial. So in some sense, if I have that a function, say, is x to the n, well, then we can actually think about reversing the power rule, okay? So if I want an antiderivative, now remember, if I take the derivative, I bring down n, and then I subtract 1 from the power of n in the exponent. So it seems like here, to reverse that process, I should add 1 to the exponent and then divide by the new exponent. So this is antiderivative. Okay, so for a power, if you want an antiderivative, then just add 1 to the power and divide by the new power. And notice that if I go backwards, if I take the derivative, I really will get back to where I started. Okay, because I'll just bring down the n plus 1, cancels with that n plus 1, and then subtract 1 from the exponent, and I'll get n. Now this works for every power of x except for 1. And the case it doesn't work is when n is equal to -1. Because if n is -1, this process actually requires division by 0, right? Because -1 plus 1 would be 0. Okay, so actually this is only true if n is not equal to -1. Alrighty, so let's just start right here. So I'm going to denote the antiderivatives by a capital letter, consistent with what the lowercase letter is. That's pretty standard. So here, what I want to do to find an antiderivative is I want to add 1 to the power. So that's going to be x to the 10th power, and then I'll divide by 10. So I should get 8 over 10 times x to the 10 for this first term. So when I take the derivative, I'll get back 8x to the 9th. And then, okay, the minus 3, that's just a constant multiple. That's not going to be affected when I take the derivative. But I'm going to need to divide by 1 more than this power. And then change x to x to the 7th. Okay, so then when I take the derivative, the 7's will cancel, and I'm left with 3x to the 6th. Same thing here, except now, instead of 12x cubed, I'll have 3x to the 4th. Okay, so I just divided 12 by the new power 4, and as you can see, just verify that if I take the derivative of capital F of x, I do indeed get little f of x. So therefore, this function I have written down here is one of the antiderivatives. Now I could also put plus 1, plus 2, plus 100, plus whatever number I want, and it would still be an antiderivative. But I might as well just use plus 0 because I'm just looking for one of them, and that is one of the antiderivatives. So I'm done. So let's do the same thing with this function, g of t. So we'll let capital G of t be the antiderivative that we're looking for. And so 3e to the t, well, the derivative of e to the t is just e to the t, and the 3 is not going to affect anything. So it looks like I can just have 3e to the t, and when I take the derivative, I'll get exactly this term, 3e to the t. Okay, and then I have plus 7. The plus 7, that's just a constant multiple. That's not going to affect anything. But I need a function whose derivative is secant squared t. But this isn't too bad. If you're really familiar with your differentiation rules, you'll remember that the derivative of tangent is secant squared. So I'll just multiply by tangent t. And I won't put plus 1 or plus 3, I'll just leave it as plus 0, so that this will be an antiderivative of little g of t, big G of t. Okay, so this is pretty simple. It's just a matter of working backwards. But I will say that this function h of r is a little tricky. This is kind of a trick problem, I would say. So if we look at this, I don't know of a function right off the top of my head whose derivative is 2 plus r squared over 1 plus r squared. Well, here's where the trick comes in. I'm going to rewrite this as 1 plus 1 plus r squared all over 1 plus r squared. Okay, so I hope you agree that that's the same. 2 really is equal to 1 plus 1. Okay, and then let's look. So I'm going to take the 1 and divide by 1 plus r squared, and then I'm going to take this 1 plus r squared and divide by 1 plus r squared. So I'm going to get 1 over 1 plus r squared plus 1 plus r squared over 1 plus r squared. Okay. Notice that r squared is always positive, so 1 plus r squared is never 0. So I really can conclude that this fraction, 1 plus r squared over 1 plus r squared, is equal to 1. So this is just 1 over 1 plus r squared plus 1. So somehow this function was just kind of compacted together, but what it really was is 1 over 1 plus r squared plus 1. And I like the function written in this form because I claim that we should probably be able to figure out what antiderivatives of these functions are. Now the tricky one is 1 over 1 plus r squared. But again, if you have your differentiation rules memorized, then you should remember that the derivative of inverse tangent of r is equal to 1 over 1 plus r squared. So the antiderivative, or one of them, will just simply be inverse tangent of r. And then I need a function whose derivative is 1 when I take the derivative with respect to r, but that's just r. So I'll leave it like that, and that is an antiderivative of this function, little h of r. Alright, so now we want to evaluate these following indefinite integrals. And now remember, this term indefinite integral was just fancy terminology for finding the most general version of an antiderivative, or the most general form of an antiderivative. So there's really nothing magical we're doing here. We're still just finding an antiderivative and sticking on a plus c at the end. And the plus c is something that is forgotten a lot, especially in later tests and on final exams. You'll give a question, here's an indefinite integral, bam, you'll knock out find an antiderivative, but you got to remember plus c. So whatever you need to do to remember that, it's very important. So let's see how this goes. So we have the integral sign here. Like I said, it is actually supposed to be an s, and we'll talk about why it is an s a little bit later. But here, okay, so I need a function whose derivative is 4 square root of t. well, here's where I'll write t as t to the 1/2. So square root of t is t to the 1/2. So when I take an antiderivative, this should be 2/3 t to the 3/2. And why do I know that? Well, remember, I add 1 to the power and then divide by the new power. So I get 3/2 as the new power, but then dividing by 3/2 is the same thing as multiplying by 2/3. Okay, so it looks like what I get here, I have 4 times 2/3 times t to the 3/2. Okay, so that's going to be an antiderivative of 4 square root of t, because if I go backwards and take the derivative, this will just be square root of t. And then minus, well, I need a function whose derivative is secant t times tan t. So think hard. This is another trig derivative. So it should be secant. So the derivative of secant t, if you recall, is secant t times tan t. Okay, so you see how knowing that your differentiation rules are really important here. And now, because I want the most general form of an antiderivative, I absolutely must put plus c. So I don't know what to do. Plus c, do not forget ever. It will cost you, maybe just 1 point on a test, but it will be very frustrating if you forget this, because it is probably the easiest points you will ever get on a calculus exam, is just remembering to put plus c. And it really is significant because it's really encompassing or getting at the heart that indefinite integrals or antiderivatives are not unique. Okay, so there's just this kind of interesting thing that derivatives, okay, if I take the derivative of a function, then I'm just going to get another function, exactly one function. But if I try to go backwards, it's almost like it doesn't have a well-defined inverse, right? It's kind of like squaring something. If I square something and then try to take a square root, well, I have to think about, was it a positive square root or a negative square root? It's the same thing with derivatives and this indefinite integral. I can take a derivative, but if I try to go backwards, I actually have infinitely many functions whose derivative is the same thing. So all that to say, don't forget the plus c. Even if you only are picking up, 25% of what I'm saying, one of the most important things you can do is just trust things until they start to make more sense. And right now, you need to trust the plus c, and don't forget it. Okay, so let's look at this function b. And right away, if you haven't seen something like this before, this looks impossible. So what is a function whose derivative is this function here? Well, this is another case of we need to rewrite it. So x cubed plus 2x squared over square root of x, well, instead I'm going to write this as x to the 1/2. Because then I can write this as x cubed over x to the 1/2 plus 2 times x squared over x to the 1/2. And then if I just use my properties of exponents, well, this is x to the 3 minus 1/2, so x to the 2.5 or 5/2, so x to the 5/2, and then plus 2, this will be x to the 1.5 or 3/2. This I can work with, right? Because I can just simply apply the power rule. So this is really equal to the indefinite integral of x to the 5/2 plus 2 x to the 3 halves dx. Okay, so all I did is just rewrite the integrand in a form that makes it really easy to see how to apply the power rule for antiderivatives. So this should be 7, let's see, no, getting ahead of myself. So we need to add 1 to the power, that'll make this 7 over 2, and then divide by 7 over 2. But that's the same thing as multiplying by 2 over 7. Okay, so again, take the derivative, we'll have 7 halves times 2 over 7 is 1, and then we'll be left with x to the 5 halves, and then plus 2, we'll have times 2 fifths, right, because this will become x to the 5 halves, and then we'll divide by 5 halves, which is the same thing as multiplying by 2 fifths. Okay, and then plus c, and we are done. So there's no magic, nothing crazy going on. Find an antiderivative and then stick on plus c, and you will be well on your way to making it. All right, so we have one more example, and by now you should kind of know the drill. So you're trying to take an antiderivative of this integrand function and then put on plus c. And so we want to write this in a way that makes it easy to see what the antiderivatives are. So this is equal to the indefinite integral of x to the minus 1 plus x to the minus second. Okay, so I'm just writing these as powers of x, and then I'll add 1 to the power, divide by the new power. Those will be antiderivatives. Okay, so x to the minus 1. Let me add 1 to the power, and then I'll be dividing by that new power. But wait, what's the new power? So if I add 1 to negative 1, I'll be left with x to the 0. And then I'll be dividing by 0. Okay, so that's a problem, right? And so if you remember, our power rule for antiderivatives, adding 1 to the power and dividing by the new power, only worked when the power was not negative 1. Okay, so how do we find the antiderivative of x to the minus 1? What is an antiderivative of x to the minus 1? Well, we actually already know the answer. So just think back and again, go through your differentiation rules and see if you can think of a function whose derivative is x to the minus 1 or 1 over x. And so, well, maybe you had to look it up, but the function is natural log of x. So if we take the derivative of natural log of x, so we just apply this d dx, so the derivative of the function natural log of x with respect to x is 1 over x. Okay, so it seems like, great, the antiderivative of x to the minus 1 is natural log of x. But believe it or not, that's not exactly right. So this is just a very small technical thing, but it's important. Okay, so remember here, this log of x, well, it's true. So the function, just think about the domain of the function, first of all. So the domain of the function is x greater than 0, right? So here we require that x be greater than 0. Okay? But we can also think about if x is less than 0. So 1 over x, what's the domain of this function? Well, everything's fine as long as x is not equal to 0. Okay? So we can also think about taking the derivative of log of minus x, where here x is less than 0. And so what's the derivative of this function? Well, we just use the chain rule. It's going to be 1 over minus x times the derivative of minus x, which is minus 1, or in other words, 1 over x. So we see that if x is positive, the antiderivative of 1 over x is natural log of x, but if x is negative, the antiderivative, or an antiderivative of 1 over x, is natural log of minus x. So an antiderivative of x to the minus 1 defined on, the same domain that 1 over x is defined on is, well, it's going to be sort of piecewise, right? It's going to be log x, so this is what the antiderivative is, if x is greater than 0, but it's going to be log of minus x if x is less than 0. But we can simply write this as natural log of absolute value of x, right? This is exactly how the absolute value function breaks up as a piecewise function. Okay, so all of that to say, kind of long-winded, but when you're taking an antiderivative of 1 over x, it's natural log of absolute value of x. And again, that's just accounting for the fact that for 1 over x, x can be positive or negative. So our antiderivative, x should also be able to be positive or negative. And so you see that if I take the absolute value of x first, I can then evaluate the logarithm. Okay, so that is the antiderivative of 1 over x, and then here we'll have minus 1 over x, so x to the minus 1 over negative 1, and then plus c. And that's the antiderivative. Or that is the indefinite integral. It's an antiderivative plus c. And of course, don't forget plus c. Okay, so now we want to do more of the same thing, but from, again, this last perspective we talked about, from the viewpoint of a differential equation. And so here, recall that IVP stands for initial value problem. So the initial value problem simply just said you're looking for a function that satisfies a differential equation and then satisfies some initial condition. Okay, so here's the initial condition. And then here, this is the differential equation. Okay, so an initial value problem requires finding a function that satisfies the differential equation and then also satisfies the initial condition. And in most cases, this will be unique. So we'll really be able to find exactly what the function is that solves this initial value problem. So the first thing I need to do is I just need to find a function, y, which is a function of x, that satisfies this equation. So I need a function whose derivative is sine x. But that's not too bad. We just got to remember our signs. So the function is going to be negative cosine x. And the reason it's negative is because the derivative of cosine is negative sine So I need this negative to cancel out that negative sign. But now, there are lots of functions that satisfy this differential equation, but they all differ by a constant plus c. Now it's our job to use the initial condition, y of 0 is equal to 1, to figure out what c is, or in other words, to figure out specifically which antiderivative satisfies this differential equation and the initial condition, i.e. is a solution of this initial value problem. So if y of 0 is 1, that means if I plug in 1 for y, and I plug in 0 for x, this should be a true equation. But now cosine of 0 is 1. So this is 1, and I have negative 1 plus c. So in other words, c is equal to 2. So my specific solution to this initial value problem is negative cosine of x plus 2. And you see that if I take the derivative of this function, I'll get sine x. And if I plug in 0 for x, I will get 1. Okay, so pretty straightforward. But again, it's going to be nice, especially if you're moving on into taking multivariable calculus or a course in differential equations, to start thinking this way. So there's just lots of different ways to think about the problems in finding antiderivatives. So let's look down here. So now notice here, we have that the derivative of a function g of t is e to the t plus 2t. And then again, we have some initial conditions. So g of t should be an antiderivative of this function. But that's pretty easy. So we have e to the t, the derivative is e to the t, and then plus t squared, because the derivative of t squared is 2t. And then I don't know which antiderivative it is, so I just have to put plus c. But now my job is to use my initial condition to figure out what c is. So if I plug in 0 for t, I should get 4. So I have e to the 0 plus 0 squared plus c. So e to the 0 is 1, 0 squared is 0. So then looks like c should be 3. Alrighty, but that means that our function g of t, the specific antiderivative we're looking for, is e to the t plus t squared plus 3. And again, you can verify that this really does satisfy the differential equation. Its derivative is e to the t plus 2t, and g of 0 is equal to 4.